All right, welcome back to AP Physics 1, AP Physics C, Unit 1 for Mechanics. I'm still focused on kinematics, and in this video, we're going to focus on average and instantaneous acceleration. So in the last video, we focused on average and instantaneous speed velocity, where our graph was a position versus time graph. But in this video, right, we're going to focus on a velocity versus time graph. Okay, velocity measured in meters per second, time measured in seconds. So one thing to remember is that the average acceleration is defined as the rate at which velocity changes. So mathematically, the definition, right, is A is equal to delta V over delta T. So acceleration is a vector, so you would have to account for the direction. Now, here's where physics teachers sometimes will confuse students. So something to note is that any acceleration that occurs will do one of three things. It'll change the velocity, right? Or excuse me, it'll change the speed, right? The magnitude of the velocity, right? Which is simply increasing or decreasing the speed. Change the direction, or do both. Now, sometimes there is the D word. And in my classroom, this is not a nice word, which if you use it in conjunction with acceleration, means that acceleration is only to speed up and the D word is to slow down. Now, any change in velocity is an acceleration. So that's the reason why, especially in my classroom, we don't use this D word, is because acceleration is the process of doing everything, not just speeding up. All right. Now, acceleration is going to be a vector that points in the same direction as the change in velocity. So this is important. Doesn't point in the same direction as the velocity, but points in the same direction as the change in velocity. Okay. So what does that mean? If I have my initial velocity here, and then I have an acceleration vector, basically what that means is I'm changing, this is my A, right? But this is actually also my delta V. I'm changing my velocity to add that much to it. So my new velocity would be bigger, right, than my initial velocity. Now you can see so that's speeding up, right? That's increasing the speed. If we're slowing down, those two vectors would act opposite each other. So here's my initial velocity. Here's my acceleration, or my delta V, or my change in acceleration, or change in velocity, which means now my velocity will be smaller, okay? And so this is my A. So it's like we're doing vector, addition and subtraction. We're simply adding A to V0 to produce our new velocity. So that's average. Now, so let's focus on instantaneous. So instantaneous acceleration is going to come from the graph, right? And it's defined as the acceleration at a specific instant in time. So if we're given so again, just like we've been talking, right? This is a secant line, which gives me the average. Now in this case, not velocity. Oops, sorry. So this would give me the average acceleration, okay? So again, secant goes to average, where if I want instantaneous, right, that's going to go back to a tangent line. In fact, if you look at it, both of these words have TAN in it, okay? So secant goes to average, instantaneous goes to tangent. But again, the slope, right? That's what this kind of looks like. The slope of a velocity versus time graph is our acceleration, okay? So how do we find that? To find the instantaneous acceleration, we're going to take the derivative of the velocity function with respect to time. So if we want instantaneous, right, we're going to do d dt of our velocity function, right? So these are kind of our two acceleration pieces, okay? So in AP Physics C, we will run into scenarios where we have non-uniform accelerations because of various reasons, right? So this would be a positive acceleration. This is when your acceleration would be 0 because it's a flat line. And this would be a negative acceleration. Okay, so let's take a look at an example problem centered around this concept of average and instantaneous acceleration. All right, so here in this example problem, we got a particle moving. It's being accelerated. It gives us what is called the functional form. The functional form is just velocity with respect to time. A v of t equals 20 meters per second times t minus 5.5 meters per second squared t squared. Okay. If you don't want the units running around, just rewrite it. So v of t equals 20t minus 10, or sorry, I was already starting to do the answer to part A. So it's minus 5t squared. All right. So part A is what is the functional form of acceleration? Part B, what is the instantaneous velocity at 3 locations, 3 times, so 1, 2, and 3 seconds. And then we're going to find the acceleration at those same 3 seconds. All right, so let's start with part A. So we know that acceleration is simply the derivative of our velocity function. Okay, so remember that comes down, we minus 1. There's a 1 here, that comes down, we minus 1. And so we end up with A of t equals 20 minus 10t. Okay, so again, remember, parabola goes to line, right? And that's what's happening here. So our velocity function is a parabola. That becomes a linear function. Okay, so there's our answer to part A. Part B, right? What is the instantaneous velocity at 3 times? So we're going to do v of 1, v of 2, v of 3. And then we're going to graph it to kind of help us predict the accelerations. So we're going to do v of 1, so 20 times 1 minus 5 times 1 squared. So it's going to give us positive 15 meters per second. Then we're going to do 2. And that's going to give us this 40, that's 20, so positive 20 meters per second. And then v of 3, so it's 60 minus 45, and that gives us 15 meters per second. So something you see here, this is the max, right, velocity. So I'm just going to kind of sketch it on our graph here. And again, this is going to help us predict or help us check our acceleration. So if I just kind of 1, 2, 3, again, I'm not doing this. All right, so 5, 10, 15, 20. So at 1 second, it was at 10, or sorry, not 10. All right, so at 1 second, it's at 15. At 2 seconds, at 20. At 3 seconds, it's 15, also 15. So our function looks something like this. Okay, and so we know that the instantaneous acceleration at these points is the slope of the tangent line. So let's predict now. So here are our 3 tangent lines. So we know at 1 second it should be positive. At 2 seconds it should be 0 because there's our flat line, and at 3 seconds it should be negative. Okay, so now let's go finish it out. So there's A, B. So now what we're going to do, we're going to do A of 1, A of 2, and then A of 3. And so we go 20 minus 10 times 1. So positive 20 meters per second squared. Perfect, because we predicted it to be positive. 20 minus 10 times 2, 0 meters per second squared. perfect because that's our flat line. And 20 minus 10 times 3, this should be 10, not 20. And that's negative 10 meters per second squared, which is perfect because we have negative slope there. Okay, so again, the analysis is very similar to the instantaneous velocity, but our focus shifts from a position versus time graph to a velocity versus time graph. In the next video, we're going to continue working here in the kinematics, and we're going to look at the cake equations.